Hi everyone. So as usual, in the description you can find a copy of these questions as well as a copy of the answer key. And at each time you can click on that and then see that exact question. So let's just go ahead and get started. So it says give the direction of a reaction if K is a lot greater than 1. So 2 greater than just means a lot greater than. So let's think about a fictitious reaction. We have AA's plus BB's in equilibrium with CC's and DD's. If we were going to write the Kc for this reaction, it would equal, assuming they're all aqueous, it would equal the concentration of C to the C, the concentration of D to the D, said another way, products, over reactants, concentration of A to the A, concentration of B to the B. So if K is much greater than 1, it means the number on top is much larger than the number on the bottom. Well, if the number on top is larger than the number on the bottom, then the products are favored in this reaction. That, in this case, the products means the forward reaction is favored because more products are made. There are greater concentrations of products than there are of reactants. Question 2 says, the equilibrium constant is given for one of the reactions below. Determine the value of the missing equilibrium constant. So we have 2SO2 plus O2 yields 2SO3, and we're given the Kc, 1.7 times 10 to the 6. Then we have SO3 in equilibrium with 1/2 of O2 and SO2. So when you have a question like this, you want to see what the difference is between this reaction and this reaction. So another way, you want to look at the one you have and then compare it to the one that you're looking for. So in this case, one thing that I noticed is that it's a reverse reaction. Here, SO3 is the product, and here SO3 is the reactant. SO2 and O2 reactants, O2 and SO2 products. So first thing we need to do is Kc equals 1 over the Kc given. And I know I'm using the same variable twice. So this is kind of the Kc that we're looking for. I'm going to put an A and a B. So the Kc we're looking for is 1 over the Kc that we're given, just to keep them separate. So now, what else is different? Well, if I notice here, I have 2, 1, 2, and here I have 1, a half, and 1. So it's also halved. So I took the reciprocal because it was in the opposite direction, right? Products became reactants, reactants became products. But now I also have half, so I need to take this to the 1/2. If your calculator is incapable of doing this, you just take the square root. It's the same thing. So this equals 1 over the square root of the Kc that we're given, which equals 1 over the square root of 1.7 times 10 to the 6. And when you do that math, you get 7.7 times 10 to the minus 4, which is choice letter E in this case. Question number 3 says, what is delta N for the following equation in relating Kc to Kp? So here, Kp involves using the pressure, and they're both gases, and Kc involves using the concentration. So what we want to look at is the change in the moles of gas. The general equation, we're not going to need it to solve this one, but it doesn't hurt to know it. Kp equals Kc times RT to the delta N, where delta N is the change in number of moles. So let's look. It's N final minus N initial. Finally, there's 2 moles of gas. Initially, there's 1 mole of gas. So I guess I should put delta N equals 2 moles finally minus 1 mole initially, which is equal to 1 mole. So delta N here is choice letter D, because we change by 1 mole of gas. So just to put it on here, delta N equals N final minus N initial, which I probably should have written above this, but I think that illustrates the point. Question 4 says, in which of the following reactions will Kc equal Kp? Well, from the previous question, you'll remember that Kp equals Kc times RT delta N, where delta N equals N final, moles of gas final, minus Ni, moles of gas initial. So if you look here, if delta N is equal to 0, then we're going to raise RT to the 0, which is going to be 1, and this whole term becomes 1. So Kp equals Kc. So if delta N equals 0, then Kc equals Kp. Well, if you look in the first case, we have 7 moles of gas on the reactant side, and we have 8 on the product side. So delta N is not 0. In the second case, we have 3 on the reactant side and 2 on the product side. Delta N is not 0. In the third case, we have 3 on the reactant side and 2 on the product side. Delta N is not 0. In the fourth case, choice letter D, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So there's 2 moles of gas, 2 moles of gas, delta N is equal to 0. Again, if delta N is equal to 0, RT to the 0 is 1, and Kp equals Kc. So choice letter D is the answer because delta N equals 0. Remember, you're counting the total number of moles of gas. Said another way, you're adding up the stoichiometric coefficients for gases. If there were reactants or products that were not gas, you would not include them. But for the gases, you would, and in this case, they're all gases, so we include all of them. Also remember that if there's no number out there, it's a 1. Number 5 says, determine the value of Kc for the following reaction if the equilibrium concentrations are as follows. So it actually gives us the equilibrium concentrations of all of the gases in the reaction. Notice that iodine is a solid, so it's not included in the Kc expression. So let's start by writing the Kc expression and then plugging in the numbers, the equilibrium concentrations that were given in the problem. So Kc is equal to the first product on the top, which is HI, concentration of HI squared, because there's 2 of them, times the concentration of Cl2, there's only 1, so we don't do anything, or we put a 1 there, however you want to think about it. So products over reactants, HCl, concentration of HCl, squared, again because there's 2 of them, and then I2 is a solid, so it does not go in the Kc expression. We have 3 gases, nothing aqueous here. So we don't put the solid in the expression. Now we can plug in. Well, the concentration of HI is given 5.6 times 10 to the minus 16. So we put in 5.6 times 10 to the minus 16, and we square that. We multiply that by the concentration of Cl2, which is given in the question as 0.0019. So we can just plug that in, 0.0019, and that's to the 1, so we don't do anything to that. And then on the bottom we have HCl, and it's squared. We find HCl is 0.13, and we square it. And when we do that, we get that the Kc is equal to 3.5 times 10 to the minus 32, which is choice letter D here. Okay, so this is how we plug in this. We don't need an ice table here because we're given the equilibrium concentrations, so we don't need to worry about finding the equilibrium concentrations. Question 6 says, consider the following reaction. Equilibrium concentrations and equilibrium constant at a particular temperature. Determine the equilibrium concentration of H2O. So if you haven't already watched question 5 or you're not sure how to do it, you're going to want to view that first because it's a similar question with a different variable essentially. So let's start by writing the Kc expression. You'll notice that everything here is a gas, so everything belongs in the Kc expression. So Kc equals the concentration of products, in this case this is ethanol, the concentration of C2H5OH. Then on the reactant side, or on the bottom, we want the concentration of C2H4, which is ethylene, and the concentration of H2O. Since there's one of everything, they're all raised to the first power, and we don't have to worry about that. Now let's plug in what we know. What we know in this case is the Kc, so 9 times 10 to the 3, because the Kc is given in the problem, so plug in, equals the concentration of ethanol, this is ethanol, is 1.69 molar, over the concentration of ethene, which is 0.015 molar, times the concentration of HCl, which is the X, which is the variable. I'm going to leave it as, oh, sorry, H2O. What am I doing? The concentration of H2O, not HCl. There was HCl as the product in the previous question. Okay, so we have the concentration of H2O. Now we need to solve this thing. The first thing that we want to do is cross multiply. So take the 0.015 times the 9 times 10 to the 3, and when you cross multiply that, you get 135 times the concentration of H2O, which is just your X, equals the 1.69, and I'm going to leave the units out because they're often left out of equilibrium type problems. Now divide both sides by 135, divide by 135, divide by 135, and you get that the concentration of H2O is equal to 0.013 molar, which is choice letter B in this case. Question number 7 says, consider the following reaction. COCl2 is in equilibrium with CO, and Cl2, everything's a gas, so everything's in the equilibrium expression, and everything's 1, so everything's raised to the first power, or said another way, we don't write an exponent. A reaction initially contains 1.6 molar COCl2. Determine the equilibrium concentration of CO if Kc for the reaction at this temperature is 8.33 times 10 to the 4. Calculate this based on the assumption that the answer is negligible compared to 1.6. This last sentence essentially tells us we don't need to use the quadratic equation. So we don't need to worry about doing that. But we do need to make an ice table. So let's start by rewriting the reaction. COCl2 is in equilibrium with, and it's a gas, CO, gas, plus Cl2, gas. And we need an ice. Initial, change, sorry, that should be a C, and equilibrium. So ice table. The initial concentration of COCl2 is given to us. It's 1.6 molar. The initial concentration of CO and the initial concentration of Cl2 are both 0 because when we start with this, and none of these have formed yet. Now, when we do this reaction, we're going to lose some amount, I'm going to call it X, of COCl2 because it's going to form CO and Cl2. Then we're going to add X amount of CO and X amount of Cl2. The equilibrium concentration is 1.6 minus X for COCl2. 0 plus X, or just X, for CO, and 0 plus X, or just X, for Cl2. Remember that this last sentence tells us that we can ignore this X and just use 1.6. We don't have to use 1.6 minus X because it's going to be negligibly small compared to this, which means we're going to lose essentially none of it outside the sig figs, or less than 5%, however you want to think about it. So now we need to write the Kc expression. So Kc is products over reactants. In this case, it's concentration of CO, the first product, over concentration Cl2, the second product, divided by the concentration of COCl2. Now I want to plug in my values. Well, I'm given the Kc, so 8.33 times 10 to the minus 4 equals the concentration of CO at equilibrium is X. The concentration of Cl2 at equilibrium is X, and the concentration of COCl2 at equilibrium, again, we're ignoring this X, is just 1.6 because we ignore this X because it's small. Now, I'm going to cross multiply here, and I'm going to multiply X times X. X times X gives me X squared, and I'm just flipping it, equals 1.6 times 8.33 times 10 to the minus 4, which is 0.00133. I am then going to take the square root. So if I take the square root of this side and the square root of this side, I get X equals 3.7 times 10 to the minus 3 molar. Technically it's plus or minus, but you can have a negative concentration. So it's going to be 3.7 times 10 to the minus 3 molar, which will give us the concentration of CO and Cl2 at equilibrium. It asks us for CO, and this is the answer, which is, in this case, choice letter. I apologize, I have a small mistake here. This should be 3.7 times 10 to the minus 2 molar, which is choice letter B. All right, I just made a writing mistake here. So it is choice letter B, 3.7 times 10 to the minus 2 molar. The next few questions are on Le Chatelier's principle. Number 8 says, consider the following reaction at equilibrium. What effect will increasing the pressure of the reaction mixture have on the system, I guess. So it looks like something got a little bit chopped off here. So let's take a look. We have Cu solid plus O2 gas yields Cu solid plus SO2 gas. So on the reactant side, we have 1 mole of gas, the O2 gas, and on the product side we have 1 mole of gas. So the increasing the pressure will favor less moles of gas, but in this case we have 1 mole of gas on both sides, so increasing the pressure will have no effect because they both have the same number of moles of gas. But generally speaking, increasing the pressure favors less moles of gas. Number 9 says, the following reaction is exothermic. What change will shift the equilibrium to the left? So if it's exothermic, we could think of heat as a product. If it was endothermic, we could think of heat as a reactant. But since it's exothermic, we could think of heat as a product. So now we want to know what change will shift the equilibrium to the left. First thing we could do is remove some O2. So we want to shift it in this direction. So if we take some O2 away, the reaction will shift to make more O2. It'll shift to restore equilibrium, and it'll say, hey, there's not enough O2. So it'll shift to form more O2. So this will cause the reaction to shift to the left. That's what we want to happen. Adding SO3. If we have more SO3, the reaction will say there's too much SO3. And to restore equilibrium, it will shift to the left. Raising the temperature. Adding heat by raising the temperature, because heat is like a product, will shift the reaction to the left and towards the reactants. So raising the temperature will shift it to the left, which means that the answer is choice letter D. All of the above will cause this reaction to shift left. All right, and the last Le Chatelier's principle question, it says, consider the following reaction. What effect will removing NO2 have on the system? So if we decrease the amount of NO2, the reaction will shift to the left in order to increase and make more NO2. So removing NO2 will cause the reaction to shift and form more NO2. So let's read the answers. The reaction will shift in the direction of the reactants, which is absolutely the case because it will shift left in this case and form more reactants. Number 11 says, which of the following is not a conjugate acid-base pair? And in this case, the H3O plus OH minus is the answer. But let's take a look. So the first one is NH4 plus. So NH4 plus losing a proton. We get NH3, so it has one less proton, and no more plus charge. And then it would be plus H3O plus if it was reacting with water, or plus H plus if you didn't show the reaction with water. So these are conjugate acid-base pair. This is the acid. It loses a proton. It loses one H and a plus charge. Let's look at the next one. H2SO3. So it loses an H, so HSO3, but it also loses a positive charge. It was neutral, so if it loses a positive charge, it's now minus. Those are a conjugate acid-base pair. Let's look at the next one. C2H3O2 minus. Now it's going to, if this loses a proton, this one doesn't have a proton to lose. In this case, this is the conjugate base and it wants the acid. So we get HC2H3O2 because this has one additional proton here, and it also went from minus to neutral, so it gained an H plus. So in this case, this is the acid and this is the conjugate base. Now let's look at this one. We have H3O plus. The conjugate base of H3O plus is H2O. It loses one H and the positive charge. It is not OH minus. These are not a conjugate acid-base pair. Now, OH minus is the conjugate base of H2O, but it is not the conjugate base of H3O plus. H3O plus can't be a base, so you're not going to have H4O2 plus. That doesn't exist, but that's basically how it works. So you want to look at adding or removing a proton in order to figure out if those are conjugate acid-base pairs. In some cases, these two cases, they gave us the acid first. In this one, they gave us the acid here, but it doesn't really matter which order they're in. You can clearly see that this one has the proton removed. So if you want to just start with this one and then see what you would get that way, you could do it in that case as well. So what's the difference? They have to be one proton different between the acid and base to be conjugate acid-base pairs. And that means an H and a plus charge. That's a proton. Number 12 says, what is the conjugate acid of HCO3 minus? So we have HCO3 minus. If you want the conjugate acid, this has to behave like a base. When this behaves like a base, it gains a proton. So it gains an H, H2CO3. So it has one more H, but it also gains a positive charge. So it goes from minus to neutral. So this is the base, and this is the conjugate acid. So if you want the conjugate acid of something, it has to behave like a base. In this case, the answer here is choice letter B. Question 13 says, give the characteristic of a strong acid. So strong acid is something like HCl, which when aqueous completely dissolves into H plus aqueous plus Cl minus aqueous. It completely dissociates in water. Or you could write it as HCl plus water yields H3O plus Cl minus. So ionizes completely in aqueous solutions. That is true. Has a polar bond. The HCl bond is covalent because they're both nonmetals. It is also polar because H is much less electronegative than Cl, so that is a polar bond. Has an equilibrium far to the right. Yes, it's not even really an equilibrium reaction. It's pretty much complete dissociation if it's a strong acid. So that is true. Has a weaker bond to hydrogen. Yes, the bond between Cl minus and H is very weak. Between Cl and H is very weak. That's why it dissociates. If you look at a weaker acid, like for example H2CO3, carbonic acid, this H is more strongly bonded, and that means it doesn't want to leave very much. If the bond to hydrogen is weak, it means it does want to leave readily. Said another way, that this pretty much completely ionizes in water. So that is the case. So in this case, the answer is all of of the above. These are all true statements about strong acids. Number 14 says, which of the following solutions would have the lowest pH? And it says, assume they are all 0.1 molar in acid at 25 degrees C, and then it gives us the Ka values. So if we have some generic acid, HA, we have HA, aqueous, plus H2O, liquid, is in equilibrium, which H3O plus, aqueous, plus A minus, aqueous. Or you could just write it as HA is in equilibrium with H plus and A minus. I'm doing it both ways on purpose because it's shown in both ways, and that way you're familiar with them. As we go out throughout this set, you'll see it in different ways. So here the Ka is products over reactants. In this case, the product is H3O plus and A minus. And the reactant is HA. Water doesn't count because it's a liquid. So this is the Ka expression. So if the Ka is high, relatively speaking, then that means the H3O plus concentration is relatively high. Low pH means high, relatively, concentration of H3O plus. So when this is high, Ka is the largest. Said another way, the one with the largest Ka value is the strongest acid and therefore has the lowest pH, which is also a perfectly reasonable way of thinking about it. It's the exact same thing, actually. So let's take a look at this. Which of these numbers is the largest? Well, what we want to look at is actually the exponents, and only look at the number on the outside if there's a tie in the exponents. Minus 2 is a far larger number than minus 4, minus 6, minus 8, whatever. It's the biggest number. So this acid is the strongest acid, and because it has the lowest Ka value, and it has the largest Ka value, and therefore it's going to have the lowest pH. Question 15 is very similar to question number 14. So if you haven't already seen question 14, I would go back and watch that. But let's take a look at question 15. It says, which of the following is the strongest base? And each of the bases is followed by the Kb value. In 14, we are looking for the strongest acid. And if you go back to that description, it's in much more detail. But here, we want the strongest base, which is the one with the largest value of Kb. So now, again, we want to look at the orders of magnitude. So here we have minus 10, minus 9, minus 4, minus 5, minus 4. So these are going to be the largest value. But absolutely, which is the largest value, is 8.6 times 10 to the minus 4 as opposed to 4.4 times 10 to the minus 4. So 8.6 times 10 to the minus 4 is the largest Kb. So therefore, it is the strongest base. Number 16 says, which of the following acids will have the strongest conjugate base? So the acid that is not a strong acid will have the strongest conjugate base. So the strong acids are HCl, hydrochloric, HI, hydroiodic, I don't know why I wrote it in this order, HBr, hydrobromic, HNO3, nitric acid, H2SO4, sulfuric acid, and HClO4, which is perchloric acid. Sometimes you'll see on this list HClO3, which is chloric acid, which is also a pretty strong acid. So these are all strong acids. These have incredibly weak conjugate bases. They like to donate protons. They don't like to accept protons. So these giving away their protons readily means that the conjugate base, in this case Cl minus, doesn't want to accept a proton. And if you look here, HBr, HCl, HNO3, and HI are all choices. The only acid on this list that's not a strong acid is HF, hydrofluoric acid. So since this is not a strong acid, F minus is a relatively strong conjugate base. There are, of course, stronger conjugate bases, but compared to this list, so relatively, it is a strong conjugate base because strong acid. These are all strong acids, so their conjugate bases are incredibly weak. Question 17 says, calculate the concentration of OH minus in a solution that contains 3.9 times 10 to the minus 4 H3O plus at 25 degrees C. Identify the solution as acidic, basic, or neutral. Well, if we look here, we have the concentration of H3O plus, and this is greater than 1 times 10 to the minus 7. So since this is greater than 1 times 10 to the minus 7, this is an acidic solution. If the H3O plus were less than 1 times 10 to the minus 7, it would be basic. Now to do the math, Kw, which is 1 times 10 to the minus 14, equals the concentration of H3O plus times the concentration of OH minus. Or in this case, divide by H3O plus, divide by H3O plus, the concentration of OH minus equals Kw divided by the concentration of H3O plus. Well, Kw is a constant, 1 times 10 to the minus 14, divided by the concentration of H3O plus, which is given to us, 3.9 times 10 to the minus 4. And when you do that math, you get 2.6 times 10 to the minus 11 molar. So this solution is acidic, and the concentration of OH minus is 2.6 times 10 to the minus 11 molar, which is choice letter A. Number 18 says, determine the pH of a 0.461 molar, this is benzoic acid, solution. If the Ka of benzoic acid is 6.5 times 10 to the minus 5. So here we need to think about the reaction of benzoic acid with water. So we have C6H5CO2H aqueous plus H2O liquid is in equilibrium with C6H5CO2 minus, so it loses the H plus, so now it becomes minus, aqueous plus H3O plus aqueous. And we're going to need an ice table, initial change and equilibrium. So it gives us the initial concentration of the benzoic acid, which is 0.461 molar, which is a very high concentration. The initial concentration of the benzoate and the H3O plus are 0 when we first do it. We're going to lose some amount, minus X amount of benzoic acid, and we're going to gain X amount of benzoate and X amount of H3O plus. Which means that at equilibrium we're going to have 0.461 minus X amount of benzoic acid, X amount of benzoate, and X amount of H3O plus. Now, we are going to assume X is small. Technically, you should calculate this, but on this practice test, I'm not going to give you any where you need to use the quadratic equation. So we're just going to assume X is small and that we can ignore it. And when something's 0.46 molar and it has a Ka times 10 to the minus 5, it's a safe assumption. Okay, so now we need to write the Ka expression. Ka equals products over reactants, the concentration of C6H5CO2 minus times the concentration of H3O plus divided by the concentration of the initial acid, benzoic acid, C6H5CO2H. Now let's plug in. The Ka is given to us. 6.5 times 10 to the minus 5 equals X times X, the equilibrium concentration of this and this are both X, divided by this one, which again we're going to ignore this X, so we're just going to plug it in as 0.461. Now we're going to cross multiply and multiply X by X, and I'm just going to switch it around. So, oh sorry, it wasn't real straight. X squared equals 0.461 times this, which is 3 times 10 to the minus 5. take the square root of this, take the square root of this, x equals, what is it? 5.5 times 10 to the minus 3 molar. So this is now the concentration of H3O plus. It can't be negative, so we're just going to take the positive answer. So now we know the concentration of H3O plus. Now we have to plug into another formula. pH equals negative log concentration of H3O plus. Or pH equals negative log of this number, 5.5 times 10 to the minus 3. pH equals 2.26. Choice letter C. This is a tremendous amount of work to solve one problem, but you do need to use the ice table to find the equilibrium concentrations of the benzoate and the hydronium ion, or H3O plus. We're going to ignore the X. Then we use the Ka expression with the X ignored to solve for the concentration of H3O plus, because it is X. We then plug into pH equals negative log H3O plus, and we find that the pH is 2.26. So this is combining a lot of ideas that you have learned in this chapter. Number 19 says, determine the Ka of an acid whose 0.294 molar solution has a pH of 2.80. So let's do an acid HA. So we have acid HA aqueous plus H2O liquid is in equilibrium with A minus aqueous and H3O plus aqueous. So let's write the Ka expression. Ka equals products over reactants, concentration of A minus over concentration of H3O plus, not over, times concentration of H3O plus over concentration of HA, like that. Now, we don't have any of this stuff except the concentration of HA. We have the concentration of HA because it's given to us, but we can find the concentration of H3O plus by using the expression, by using the pH from the expression, concentration of H3O plus equals 10 to the negative pH, which equals 10 to the negative 2.80. So the concentration of H3O plus is equal to 0.00158 molar. Because the stoichiometry is 1:1, the concentration of A minus must also equal 0.00158 molar. What about the concentration of HA? Technically speaking, it's 2.94 minus this, but this is like less than 1% of this, so we can kind of just ignore it. In fact, I'm going to just ignore it. So in this case, we can plug in. The concentration of A minus and H3O plus are the same, so it's 0.00158 times 0.00158. They're again the same because for every one H3O plus that we make one A minus, so the concentrations must be equal. Divided by the concentration of the HA, which is 0.294. Now if you want to do 0.294 minus 0.00158, that'll work too. Okay, you'll get the same answer, but this is less than 1%, so we don't have to, it's way less than 5%, so we can just ignore it. When you do that math, we get 8.5 times 10 to the minus 6 for the Ka, which is choice, in this case, choice letter C. In the previous questions, we've looked at acids. Now we're going to look at a couple questions that deal with bases. It says, determine the pH of a 0.35 molar NaOH solution. Well, NaOH is a strong base, which can completely dissociates. NaOH solid becomes Na plus OH minus. And these are both aqueous. Said another way, the concentration of NaOH is equal to the concentration of OH minus, which in this case is equal to 0.235 molar. So this is the concentration of OH minus. So now there's lots of ways we can do this. I'm going to calculate the POH. The POH equals the negative log of the OH minus concentration. So the POH in our case equals the negative log of 0.235, and the POH equals 0.629. Sorry, my computer's telling me I have to restart. Now, I'm not asked for the POH, I'm asked for the pH. So I have to convert this. Well, we need to remember that the pH plus the POH equals 14. Or said another way, the pH equals 14 minus the POH. So the pH equals 14 minus 0.629. The pH is equal to 13.37. And that, in this case, is choice letter E. It is worth noting that if you wanted to, you could calculate the concentration of H3O plus using the Kw and then plug it into the pH equals negative log of concentration of H3O plus. You would get the exact same answer if you do it that way. I don't know that either one is faster or better. This is just the way that I chose to do it. All right, question number 21, which is very similar to question number 18 if you haven't seen that already, except it's using a base. It says determine the POH of a 0.188 molar NH3 solution at 25 degrees C. And it gives us the Kb of NH3 is 1.76 times 10 to the minus 5. So in this case, NH3 is a base, ammonia is a base. So NH3 aqueous is in equilibrium, H2O, liquid is in equilibrium with NH4 plus aqueous, so it gains a proton from water, plus OH minus aqueous. So this is just a base, and we can use an ice table again, just like we did in a previous problem. So in this case, the initial concentration of NH3 is given 0.188 molar. The initial concentration of NH4 plus and OH minus is 0. We're going to lose X amount of NH3, and we're going to gain X amount of NH4 and X amount of OH minus. So at equilibrium, we're going to have 0.188 minus X NH3. We're going to have X NH4 and X OH minus. However, we're going to ignore the X here because X is going to be relatively small. Said another way, we're not going to use the quadratic equation. Now technically, I think on ALEKS, they ask you to check to make sure that it's less than 5%. But here, I'm not going to give you any where you have to use the quadratic equation. Let's write the Kb expression. So Kb, just like Ka, is products over reactants. In this case, NH4 plus OH minus over NH3. Plugging in what we know. Well, we're given the Kb, 1.76 times 10 to the minus 5 equals X times X, because the equilibrium concentrations of these are unknown, over 0.188. Note that we have ignored this X because we consider it to be relatively small compared to the initial concentration. What we end up with is X squared, X times X, equals 0.188 times this, which comes out to be 3.31 times 10 to the minus 6. Take the square root, take the square root, take the positive answer. X equals 1.18 times 10 to the minus 3 molar. Now we know the concentration of OH minus, but it doesn't ask us for the concentration of OH minus, it asks us for the POH. Well, we need to remember that POH equals negative log of the concentration of OH minus. So the POH equals negative log of this answer, 1.18 times 10 to the minus 3 molar. And the POH, in this case, equals 2.740, which is, in this case, choice letter E. Again, quite a bit of work to solve a single problem. Number 22 says, determine the Ka for CH3 NH3 plus, protonated methylamine, at 25 degrees C. And then it gives us the Kb. Well, what we need to remember is that the Ka times the Kb equals Kw, which is a constant, 1 times 10 to the minus 14. Said another way, if I divide both sides by Kb, Ka equals Kw divided by Kb. Well, Kw is a constant, 1 times 10 to the minus 14. And the Kb in this case is given 4.4 times 10 to the minus 4. When I do that math, I get 2.3 times 10 to the minus 11, which is choice letter A. All right, so the last one, number 23. It says find the percent ionization of a 0.337 molar HF solution. And it gives us the Ka for HF. This question is somewhat similar to a previous question that we did, I believe, I want to say number 18 or 19. And basically, we have to do a similar thing, except in that case, we're asked for the pH, and in this case, we're looking for the percent ionization. So we have to do it a little bit differently at the end. But basically, what we have is weak acid, HF, aqueous, reacting with water, liquid, to form H3O plus, aqueous, plus F minus, aqueous. And we also need to remember that the percent ionization is equal to the concentration of H3O plus at equilibrium divided by the concentration of HF initial times 100, because it's a percentage, so we have to multiply it by 100. So we need to do an ice table again. So we need initial, change, and equilibrium, because we need the equilibrium concentration of H3O plus. In the previous example, we used it to find the pH. Here we're going to use it to find the percent ionization. It's just a different calculation, but it's basically the same thing. They're not the same value, but it's a very similar process, except we plug it in here instead of the pH equation. All right, so starting with the initial concentration of this, well, this is given in our problem. It's 0.337 molar. There's no H3O plus and there's no F minus. We're going to lose X amount of HF. We're going to gain X amount of H3O plus and X amount of F minus. At an equilibrium, we're going to have 0.337 minus X, but we're going to ignore X, so we don't have to use the quadratic, and because it's going to be relatively small, less than 5% of the values of X. We're going to have plus X here, sorry, we're going to have X here, and X here. Now we can plug into the Ka expression. Ka equals the concentration of H3O plus times the concentration of F minus divided by the concentration of HF, like this. Now the Ka is given, so we plug that in. 3.5 times 10 to the minus 4. Notice that this is two significant figures, which is going to limit our answer to two significant figures at the end. Then H3O plus is X, F minus is X, and as we have done several times in previous questions, we're going to ignore the X in this term here. So one thing, we don't have to use the quadratic equation, and another thing is it's less than 5%. So we're just going to plug this in as 0.337. Cross multiply, X squared equals this times this, which is equal to 0.000118. Take the square root, and we find that X equals 0.0109 molar. Okay, we again only take the positive answer. This means at equilibrium, the concentration of H3O plus is 0.0109 molar, which in the previous problem, again, we can plug into the pH equation to find the pH of the solution, but that's not what we're asked for. We're asked for the percent ionization. So in this case, the percent ionization equals the H3O plus concentration, 0.0109 molar. You don't really need to write the units. Divided by the HF initial concentration, 0.337 molar, times 100. Remember that this is 2 sig figs, so our answer is 2 sig figs. When you do this math, you find that the percent ionization is 3.2%. So percent ionization is found in a very similar way to pH how the pH would be found. It's just a different calculation at the end. So practicing this will help you with both types of questions. So that'll do it for this problem set. Below in the description again, you can find a copy of the answers. You can also find a copy of the original questions as well as the times in case there's specific questions that you're interested in watching. I do appreciate you watching, and good luck on your test.